because our speaker, yes, now I hear myself. Okay, is Raffaele Vitolo from the University of Salento, and he will tell us about relations between projective geometry, homogeneous Hamiltonian operators, and integrable systems. Raf, you're welcome.
Oh, thank you very much. It's a pleasure.
Again, no, Raf, we do not hear you.
Okay, can you hear me now?
Now, yes.
All right. Yes, I have a problem with the microphone. I don't know why, but the volume of the microphone keeps going down. Okay, if you have troubles, please stop me.
Okay, please begin.
All right. So today, do you see my screen? Can I start?
Yes, we see.
Okay, so today I will speak you about the projective geometry of a certain class of Hamiltonian operators. This is not the first talk on this general topic, but it is the first that I delivered at the independent university on this particular class. So it's a follow-up with respect to previous talks that I delivered again on the projective geometry of Hamiltonian operators. And there are new interesting developments. I would like to excuse myself to those who already might have listened to this talk, because I delivered it in the last months in a couple of places. So maybe it's not something entirely new for everybody, but this is what I have ready at the moment. And okay, in the near future, I might deliver another seminar on a different topic. Okay, so I start with a kind of summary on the theory of Hamiltonian operators, even if I guess that everybody in the audience know about what I'm going to say in this slide. I will deal with Hamiltonian formalism for evolutionary systems of PDEs. And a Hamiltonian formulation of an evolutionary PDE is rewriting a reformulation of the evolutionary system at hand, as it is written here in the middle of the page. Aij applied to the variational derivative of a certain functional. This functional is called the Hamiltonian density, and Aij is a matrix differential operator in total derivatives. Here we are dealing with partial differential equations where dependent variables, so unknown functions, depend only on two independent variables, t and x. The matrix differential operator Aij is a Hamiltonian operator if it provides a Poisson bracket between functionals. The Poisson bracket is defined as the lowest displayed equation here. In order for this to be a Poisson bracket, it must be bilinear, but it is evidently bilinear. And then it must be skew symmetric, and the Jacobi property should hold. Skew symmetric means that the operator is formally square joined, because you might be able to bring this total derivative to the other side with no effect. Else then a change in sign. of course, this integral with respect to the x means that all expressions, the integrand indeed, the expression which is in the integrand should be considered up to total derivatives, total x derivatives. So these are the main differences between the finite dimensional Hamiltonian formalism and Hamiltonian formalism for PDEs. The fact that the operator is not algebraic, it's a differential operator. And the fact that the bracket is defined up to total derivatives via the operator, the action of the operator. So now we consider a class of operators which is quite popular in different contexts. It was introduced in 1983 by two great Russian mathematicians, Boris Dubrovin and Sergei Novikov. And this class was introduced how to say, having in mind as a first example Euler equation for perfect fluids, which is a system of PDEs of quasi-linear type. So it's of the same type as the PDE, the evolutionary PDE that you see here. So there is a matrix. Each entry of the matrix is an algebraic expression of the field variables, and this matrix is multiplied by x velocities. So x derivatives, first order x derivatives. There are many examples of such equations which are Hamiltonian with respect to an operator of the class that was introduced by Dubrovin and Novikov. And such an operator has the form which is in the red box here, displayed formula. And when you consider each summand of the operator, you notice that there is exactly one x derivative in each summand, here and here. And you can assign a grading to x derivatives, and then you would say that this operator has degree homogeneity degree 1. This is called homogeneity degree. And the effect of requiring that the operator is homogeneous is that if you change dependent variables into new dependent variables, so if you do a transformation of the dependent variables only, the form of the operator will remain unchanged. Moreover, it might be seen that under such transformations, the component of the operator, so Gij, the matrix Gij, and the indexed object Bijk, transform as geometric objects. So in particular, this Gij, the leading coefficient matrix of the first order operator, the first order Hamiltonian operator, transforms as a contravariant tensor, and this how to say indexed family of functions Bijk transform as the coefficient of a linear connection, the Christoffel symbols of a linear connection. Normally, Christoffel symbols have two low indices and one upper index, but here you can assume that this is how to say a raised index version of the Christoffel symbols with a minus sign. And so under a change of coordinates, this object transforms as a how to say a Christoffel symbol with raised index would do. Then one could prove, let me see next slide. No, okay. It's still not the moment to change the slide. So one could prove that under requirement of A1 to be a Hamiltonian operator, so the matrix of differential operators A1 ij, So if you require that is a Hamiltonian operator, then it turns out that Gij is a contravariant flat pseudo-Riemannian metric, and Bij are its Christoffel symbols. So since you see there is geometry, you require that the operator is form invariant, and then suddenly it turns out that you have geometric properties of the coefficients. So what happens is that you can choose special coordinate systems in which the operator has a canonical form, and for such geometry, it's clear that since the matrix, the pseudo-Riemannian metric is flat, you can choose flat coordinates. In flat coordinates, everything becomes either constant or zero. This means that the pseudo-Riemannian metric becomes constant. I call it eta ij. And correspondingly, the Christoffel symbols, even in the upper index version, they turn out to be zero. Next, we have the higher order homogeneous operators. What are these? They were introduced by Dubrovin and Novikov as a generalization of first order homogeneous operators. In the beginning, they played, how to say, some, in a sense, not such a major role. But now we will see today, well, after a while, it turned out that they found many applications in different subjects in integrable systems. We will discuss some of these applications. So what I would like to discuss in this talk today is the geometry of higher order homogeneous operators, and in particular of second order operators. I already discussed the geometric properties of third order homogeneous operators in this seminar. I would like today to speak about, how to say, next iteration. So the geometric properties of second order operators. Second order homogeneous operators have two x derivatives in each summand, as you can see, while third order homogeneous operators have three x derivatives in each summand, as again you can see. Now let us focus. So you see that these operators have quite a long and complicated expression. So at the moment, we can only say that if we change coordinates, as I said, so dependent variables into new dependent variables, the form of the operators will remain the same. The point is that under this change of coordinates, both the leading coefficients will change coordinates as contravariant tensors. Then there is another interesting feature. So we have seen that in first order operators there are Christoffel symbols of a linear connection up to index raising one index. Then what happens here is that the two coefficients here in the part of the operator which is of zero order with respect to derivatives, so there is no Vx in the sense of operator here in this bit, and the coefficient of the highest order derivative is again transforms as a linear connection, and the same happens for this coefficient into the third order operator. So we have linear connections in all, geometrically speaking, in all such homogeneous operators. Indeed, one can show that this is a general property. But then how these connections will behave if one requires that the operators are Hamiltonian? Then what happens is that, oh, sorry, let us stay here. What happens is that it might be proved, it was proved independently by Gennady Potyomin and Doyle, Peter Doyle, I think, that that such coefficients indeed are linear connections which are symmetric and flat. And this holds for every order. There exist flat coordinates for every higher order homogeneous operators. And in the flat coordinates, the operators assume quite a simple form, so they can be very much simplified. But let us discuss a kind of application of such homogeneous operators. So where do we see higher order homogeneous operators together, coupled together with first order operators? We see them in, well, in a lot of integrable systems, because what happens is that there are integrable systems which are defined by bi-Hamiltonian pairs, so pairs of Hamiltonian operators, where one of the Hamiltonian operators further decomposes into the sum of a first order homogeneous operator and a higher order homogeneous operator. So this is a mechanism which I call, or many other people call, the mechanism of compatible triples. And it is quite a frequent mechanism in the field of integrable systems. As everybody knows, a bi-Hamiltonian pair determines an integrable system. Here we consider bi-Hamiltonian pairs which are made in the following way. You have two first order homogeneous Hamiltonian operators and a third higher order homogeneous Hamiltonian operator, which might be second order, third order, or even a combination of the two. And then if you consider bi-Hamiltonian pairs which are indeed triples of operators, where one of the operators is first order and the other operator is the sum of a first order plus a higher order operator, then there are many integrable systems, famous integrable systems of this form. For example, KDV, Kamasa-Holm, dispersive water waves, which is a two-component system, coupled Harry-Dean, which is a two-component system. All these with a higher order homogeneous operator, which is of order 3, so a third order operator. And then with second order operators, there is AKNS system, two-component Kamasa-Holm, Kaup-Brewer equation, S formulated by Cooper-Schmidt, and others. Okay, but we can consider also in a much more simple way compatible pairs, which are made by a third order operator and a compatible first order operator, or a second order operator and a compatible first order operator. So there are examples in the first category. So examples in the class of bi-Hamiltonian systems where one of the operators is purely third order. And these are basically Monge-Ampere equations, WDVV equations, oriented associativity equation. And the number of examples is quite small, to tell the truth. Okay, in this talk, I will show you that also second order operators can be at least admit integrable systems which are Hamiltonian with respect to purely second homogeneity degree Hamiltonian operators. This is something completely new. Okay, so I just would like to say that I introduced the name regular mechanism for triples and singular mechanism for pairs because the problem is that pairs are much more rare than triples. Triples are much more common in the examples of as examples of integrable systems. So while pairs are quite rare, and indeed I cheated a little bit because if you consider second order operators and try to consider first order compatible operators, which are which are compatible with respect to fixed second order operator, you usually find nothing find nothing in the local class. You have to introduce non-local first order operator to find something non-trivial. And but this is a completely open problem at the moment. Okay, we will see it in much more details. Let me explain by means of examples what do I mean by Hamiltonian structure from compatible triples. So a classification was started by Lorenzoni, Savoldi, and myself a few years ago. And the main example is KdV equation, where you have that one operator of first order homogeneous is just dx. Second operator first order homogeneous is 2u dx plus ux. And the third order homogeneous operator is just the cube. Then you can combine these three operators in two ways. If you combine them into a pencil where the parameter is lambda, here epsilon squared is a dispersion parameter, then you obtain the pencil of KdV. While if you combine these two operators in another way, so you move the first order operator, so you isolate Q1 and you move P1 together with A3, so you create a different pencil, then you have the Kamasa-Holm hierarchy. Okay, so you understand how to combine three operators into a pencil and how to get an integrable system in this way. But we are interested in this talk into second order operators. In order to have a non-trivial second order operator, you need at least two components, because the problem with the second order operator is that the leading coefficient matrix, due to square jointness, is co-symmetric. So it's a symmetric contravariant to tensor. And this okay, this has rank maximal rank only in two component case at least. If you consider the one component case, you just get 0, so not interesting. Okay, so here I brought the example of a trio of operators that can be combined in two pencils. The two pencils are the pencil of A, K, and S, and the pencil of two-component Kamasa-Holm hierarchy, which was both were studied by different authors. Okay, so you see how a second-order operator enters into the creation of integrable systems. So if you are able to classify the geometrically by some geometric property, the second-order operator, you can classify the pencil, the first-order operator, and the pencils. The same happens for third order operator, and we did exactly this together with Paolo Lorenzoni and Andrea Savoldi. Now we make a step more towards the classification of second order operators. So basically the aims of the talk are to give new geometric properties, which are projective geometric indeed, of second order homogeneous Hamiltonian operators. Then we will present a classification of such operators with respect to the action of projective group, which represents itself as a group of reciprocal transformations, and then describe the corresponding Hamiltonian systems, which are Hamiltonian with respect to second order operators, and then compare the results that we obtained to the results that we obtained several years ago together with Jennifer Aponte and Maxim Pavlov. In the case of third order homogeneous operators, they share a lot of properties, not all, but this let us think that there is a kind of general picture in the background, which we still did not discover, at least completely. Okay, so as I said, there are two flat connections in both. So there are flat connections in both the second order operators and the third order operators in the homogeneous case, of course. So we can use flat coordinates, and the description of the operators in flat coordinates is very much simplified and reduced. And in the case of second-order operators, the operator factorizes in this way. So the X composition, a matrix of functions, so that no derivatives here, composition dx again. And in the third-order case, the operator decomposes in a very similar way. Of course, in the middle, there is something more complicated. So we can use flat coordinates and simplify the operators, both families, both orders. Now let us consider second order operators. So in the second order operators, what we would like to show, what I would like to show is the structure of GIJ. GIJ, in the non-degenerate case, we always will consider in this talk, even from the very beginning, the non-degenerate case. Non-degenerate means that the leading coefficient matrix has non-vanishing determinant. In particular, so the determinant of GIJ is different from 0. In this case, when you invert this matrix, you have a matrix of linear functions. There is one more property. As I told you, Gij is symmetric. So this expression is symmetric with respect to Gij, but there is a plus, there is something more. Tijk is totally symmetric with respect to all the indices. This is part of the Hamiltonian property of the operator A2. There are no further properties. Okay, so the idea is, you see, we proved together with Jennifer Pond and Maxim Pavlov in a series of papers that there is projective geometric invariance of third-order operators. So the idea was, is there a projective geometric invariance also here? The answer is yes. What happens is that the operators are form invariant, the second-order operators, with respect to reciprocal projective transformations. So what are reciprocal projective transformations? These are transformations which are projective with respect to independent variables. So they are projective in the sense that they are linear forms divided by a fixed linear form. Each expression of the new independent variable in terms of the old ones. But then you have to couple this transformation together with a non-local transformation of the independent variable x. So the x tilde, the new independent variable, is the linear form, which is the denominator of the projective transformation, multiplied by the x, the old independent variable x. So such a transformation preserves the canonical form, and indeed one could quite easily show that the leading coefficient matrix is transformed in lower indices in a conformal way. So it will be transformed in a new coefficient matrix which has the same structure. So this G tilde 2 Ij has the same structure as G Ij. But there is a conformal factor, 1 over delta cube. This delta is again the, how to say this, denominator of the projective transformation. Point is that this delta cube can be totally removed using the fact that there is delta multiplying the x. So when you invert this matrix, we have delta cube to the numerator, but then there will be a delta in the denominator 3 times because you have it here, here, and then also this is there is a density involved because it's a Hamiltonian operator. So this delta cube in the denominator will disappear, and the new operator, the newly transformed operator, will have exactly the same form as the old one. Okay, but then how to relate this second order operator to an object that has been classified, so that we can have a bijection, and by a classification of a certain geometric object which is known, find the classification of the second order operator. This is the idea. So well, we introduced a new notation, and we incorporated this G0 JK into the T's. If you remember, let me show it to you. Okay, so this was the expression of the of the coefficients of the operator in lower indices. Basically, what we assume is that we can these UK are indeed affine coordinates in a projective space. So they indeed are the ratio between Vk and Vn plus 1. So if we multiply by Vn plus 1, we obtain just a linear expression with totally symmetric coefficients of of the projective of the coordinates in the projective space, of the homogeneous coordinates of a projective space. This is what we would like to have. And indeed, if we introduce this new notation, so if we treat all coefficients on the same footing, in a sense, then we can prove that a projective reciprocal transformation will produce a transformation of this type. It's a kind of conformal transformation of a 3 tensor, of a covariant 3 tensor. Which is, by the way, totally symmetric with respect to the 3 indices. Keep in mind that the Greek indices have a longer range. The range is extended by 1 to the right. So the range goes from 1 to n plus 1. And then we can identify a 3 form with a 2 form which has coefficients which are linear with respect to dependent variable in this way. And so you understand that now we can map every leading coefficient in lower indices of a second order Hamiltonian operator into a 3 form, and conversely there is a bijection, complete bijection. The point is that luckily 3 forms have been classified under the action of the projective group. So we will get results from algebraic geometers and algebraists for free in our framework. So this is the theorem formalized, which I basically already told you just a few minutes ago. There is a bijective correspondence between homogeneous second-order Hamiltonian operators in canonical form in dimension n and 3 forms in Cn plus 1. The bijective correspondence is preserved by projective reciprocal transformations up to a conformal factor. Okay, so now let us try to understand what is the geometric, the algebraic variety, which underlies the Hamiltonian operator as a 3 form. Let me do some summary. Basically, it can be proved that every 3 form in Cn plus 1 yields a certain type of algebraic variety, which is called a linear line congruence. This is not our finding. It is a known fact in the literature, and there is a paper which was fundamental for us. I will tell you about this paper a little bit later. First of all, let us see how can it be that a 3 form yields a linear line congruence, because a linear line congruence is a variety in the space of lines of a certain projective space. So you should pass from the projective space to the space of its lines. And this is done through the Plucker embedding. So basically, if you take 2 points in a projective space, and then there will be expressions which give sort of coordinates of the line, which goes through U and V. So these are the determinants of all minors of the matrix, which is formed by U and V as 2 rows or 2 columns. In this way, you can consider P lambda 2 of Cn+1 as containing all lines of a projective space. So it's not exactly here that you embed the projective space into the space of all lines, but basically you embed all lines. Every line corresponds to a point here in the projective space of the second wedge of Cn+1. Now, if we consider a 3-form in n+1, then we can consider a system of equations where to every line in Cn+1, and the line is just how to say a plane into the space which defines then the projective space. To every line, you contract the line with the 3-form, you get a system. Let us check the coordinate expression. It's quite simple. So this is a line you contract with a 3-form and you obtain a system of this form. So if you think of this P mu nu as an unknown, as a coordinate in this projective space, then this is a system of linear equations into the projective space. Now, the space of all lines is not the whole projective space, but it is just the Grassmannian. So basically, this corresponds to all decomposable elements, so all points in the projective space which are given by decomposable elements into this wedge product. And it corresponds to the space of lines in the initial projective space. And if you cut this Grassmannian with the system of equations contraction of omega by L equals 0, then you obtain in the generic situation a linear line congruence. Let me be cautious because generic situation here means that it is not always the case that the system, linear system that we discussed intersects cleanly the Grassmannian. There is a complete discussion in this sense into the paper that I was mentioning to you before. This paper was written by De Poi, Faenzi, Mezzetti, and Ranestad, and it was published quite recently. There is a geometric properties of all linear line congruencies, which are defined in this way. Line congruence is an old terminology dating back to probably Castelnuovo, I don't remember. Linear, because it's a family of lines, so a congruence of lines, which is selected by linear equations. The linear equations are given by our 3-form. By the way, this is a Fano variety. For the algebraic geometers, this is interesting. So now the classification, which for us it's probably more important. So 3 forms are classified under the action of the projective group. You can find this classification for basic dimensions in a book by Gurevich, which is called The Classical Theory of Invariance, probably. So in our case, n must be even, because we required the form to have maximal rank. So we require the form to be non-degenerate. And this is only possible if we are in even dimension. Now in dimension 2, we have only one operator, which corresponds to the constant, to the only 3 form that we have. And the operator is the operator that you already have seen. This operator corresponds to the operator 0, d square x minus d square x and 0. It is the operator that defines the triple for AK and S or for two-component Kamasa form. Okay, but then now we jump to n equals 4. So this is, in my opinion, this is the main reason why people never studied in detail the theory of second-order operators. The point is that there is nothing in between two components and three components if you require non-degeneracy. And then in four components, everything is difficult. Computations are very difficult. And examples are difficult to find, to deal with them. It's difficult. So this is probably a reason why this this class was not, how to say, not under the attention of any other researchers until now. In n equals 4, you have only one orbit in the classification, and there is a representative which is this free form here, and this free form defines a non-degenerate operator, which is the constant operator. So again, not so exciting, but we should always find such an operator in our classification, so there is coherence until now. And then we jump to n equals 6, and there are several orbits here. The most general orbit has no parameters inside, and we can project it into the affine space and obtain, after a sequence of operations, this three form here, sorry, these two form here, which depends on coordinates. It's the representation of a three form as a two form depending, linearly depending on coordinates. And you can see that this is non-trivial, non-constant, and it has a determinant which is a perfect square because it's a skew-symmetric matrix. So the square root of the determinant is the Pfaffian of the square of the skew-symmetric matrix. And this, when the Pfaffian is equal to 0, you have a jump in the dimension of the linear line congruence. So it's no longer a linear line a Klein linear line congruence. It's a degenerate locus of the congruence. So it has a geometric meaning. It is preserved by reciprocal projective transformations. So there are four more closed orbits, and the simplest one contains the constant operator. So this operator that you see here cannot be brought to constant form by a reciprocal projective transformation. So you see that the first completely non-trivial instance is in dimension 6, so it's quite complicated in a pre-computer approach. In the highest dimension that we had been able to find in the literature was studied by Wimberg and Delashvili in 1988. It was published in 1988, and the classification is quite involved. First of all, every free form can be represented as the sum of a semi-simple and a nilpotent element, which are such that their wedge product is 0. This is called Jordan decomposition, and all the semi-simple three vectors can be generated by linear combinations of four elements. The four elements are described here. The linear combinations are not arbitrary. You have to assume a system of inequalities on the linear combinations, but this still means that you have a dimension 4 orbit because there are inequalities on the parameters lambdas. So these are not equalities. So you have a four-dimensional orbit. So this is the first dimension, n equals 8, where you have a non-point orbit, an orbit which does not reduce to a single point under the action of the projective group. And then, unfortunately or fortunately, in this case, you have 132 classes of non-trivial three vectors, and this means a lot. We couldn't list all of them in our preprint, Of course, when you raise the dimension, no classification makes sense because you have simply too many representatives, too many parameters, and we stopped here also because this is a matter for algebra, is not for us. Then, so what happens if we let a projective, reciprocal projective transformation act on a triple? So we know that the second order and third order homogeneous operators stay the same. They have the same form after such a transformation. But what happens to first order operators is that since the transformation is non-local, the differential of x transforms into a non-integrable way. So this is not the transformation of x tilde into something function which gives you then this relationship between differentials. So it's not holonomic. And this means that any local first order homogeneous operator transforms into a non-local first order homogeneous operator of Faraponto form. So if you want to classify triples using projective classification, which is the strongest classification that we have, so it has the orbits of smallest dimension. Unfortunately, you have to resort to the use of non-local first-order operators, which is perfectly legitimate. We only did so far in the past classification of triples with local operators because we used two-component affine classification of third order and second order operators. And second order was quite trivial because in two components we had only one simple operator. Extension of this program to third order, fourth order, three component, four component operators is now possible because we have software, and there is software for such calculations of with the non-local operators of Faraponto type. So it's an open problem indeed. So we found second order Hamiltonian operator. What about systems which are Hamiltonian with respect to such second order operators? Well, we have been able to find them all. Let us see how did we do. We did it using well, conditions which are straightforward generalization of those of Zaryov for first order homogeneous operators. The conditions which Zaryov found on first order homogeneous operators to be the Hamiltonian operators of a quasi-linear first order system are these two conditions here. So G1 is the metric of the leading coefficient matrix of the first order operator, and here this nabla is the Levi-Civita connection with respect to the covariant tensor corresponding to this contravariant to tensor, so the inverse of this. So you have a symmetry property of the covariant derivative and then a symmetry property of Vjk as a 1-1 tensor with respect to this contravariant metric. So how to generalize this result? Zaryov used Hamiltonian. We used a completely different way because finding Hamiltonian for second order operators, for third order operators proved to be much more difficult because you have to use non-local Hamiltonians. So then finding the right answers is absolutely unclear. It's much better to use a technique which was invented by Paul Kersten, Joseph Krasicek, and Alec Verbowiecki many years ago, and use such a technique in order to find equations that put in relationship Hamiltonian operators with respect to systems and say when a Hamiltonian operator is the Hamiltonian operator of a certain system of PDEs. We work in the case of quasi-linear first-order systems of PDEs or systems of PDEs of hydrodynamic type. And we have been able to find these two systems. The first two rows are for second order operators. Be careful because I use systems which are systems of conservation laws. So here we have that Vij is indeed the derivative of Vi with respect to Uj multiplied by Ujx. So this is the total x derivative of a flux to the right hand side. These two relationships are the relationship that gives compatibility between second order operator and a hydrodynamic type system, and these were found in 2018 for third order operators. Sorry, here it's wrong. It should have been written. This is third order homogeneous operator. So there is one equation in addition to the system that I wrote here above for second order operator. For third order operators, the system is more complicated. There is a further set of equations. Okay, now this system in case of second order operators can be completely solved. And the solution is here. What happens is that, first of all, if you fix the operator, you can find all possible fluxes. And the fluxes have this form, where Wjl is a constant matrix, symmetric. Bj is an arbitrary vector. This is a linear expression multiplied by the leading coefficient matrix in upper indices. And this gives you a vector of fluxes, which are rational expressions, so nonlinear expressions of the U's. Another interesting fact is that the eigenvalues of the Jacobian of the fluxes are double. So this is not a strictly hyperbolic system. Unfortunately, the system which are Hamiltonian with respect to second order operators have double eigenvalues, always. Then, as I told you, the Hamiltonian is non-local. So if we introduce new non-potential variables, you can write down the Hamiltonian in this way. There is Bs here. This Bs spoils everything in the sense that it makes the Hamiltonian non-local into a non-local expression. Another geometrically interesting thing is that if you compute the Hantjes tensor of the fluxes of the system, of the Jacobian of the fluxes of the system, it vanishes identically at every dimension. We cannot conclude that the systems are diagonalizable because since the eigenvalues are double, the point is that there might be not enough eigenvectors. If there are enough eigenvectors and the Hantjes tensor vanishes, then we can conclude that the systems are diagonalizable. This happens in numerical experiments, in computational experiments. If we fix all these parameters W and B's and fix a second order operator randomly chosen in 4 components, in 6 components, maybe also in 8 components, I don't remember, we can find double eigenvalues and double eigenvectors, so 2 independent eigenvectors for every eigenvalue, and then the system is diagonalizable. Since the system is diagonalizable and it is a system of conservation laws, it is automatically semi-Hamiltonian due to a theorem by Seveneck. Seveneck was a student of Serre, probably. Another interesting thing is that the system of conservation laws that we obtain can be identified with linear line congruencies, but the dimension of the linear line congruencies is 1 more with respect to the dimension of the linear line congruence of the Hamiltonian operator. Due to a theorem by Agafonov and Ferapontov, the systems are linearly degenerate. So the systems are linearly degenerate, then they are linearizable when n equals 4. One non-linearizable system when n equals 6, a non-linearizable 4-parameter family when n equals 8, Sorry, probably here there are more classes of non-linearizable systems. Now I don't remember, maybe 2 or 3. Okay, and then there is a multi-parameter family of non-linearizable systems. When I say non-linearizable or linearizable, I always mean linearizable or non-linearizable with respect to projective reciprocal transformation, which is the group that we are considering now. So, as I told you, experiments show that random systems are diagonalizable. We have not been able to provide a general theorem that says that all double eigenvectors have all double eigenvalues have double eigenvector. Unfortunately, we have no such a theorem. But all the systems that we analyzed are integrable because they are semi-Hamiltonian. They are integrable by Tsarev method of generalized autograph transformation, even if one should be also cautious with respect to this method because the use of this method, because the use of this method was developed for systems which are strictly hyperbolic, so all eigenvalues different. By some experiments, it seems that the method can work also for systems which are doubly degenerate, in these cases at least. But again, no general result in this sense, only very strong suspects. So one example of one of those systems is here, you can see it. There are several constants in the system, and the system is defined by this operator, even if this is an example which we wrote down before knowing that such a system can be linearized by a projective reciprocal transformation. However, also the non-linearizable systems have a very similar look. So they have fluxes which are rational functions. So you can compute the degrees, it's in our paper. Okay. When I say our paper, I wrote 2 papers on this topic with Pierandrea Vergallo, who was my former PhD student. One of the papers has been published in DGA, Differential Geometry and its Applications, and another one is in archive. You can find it if you're interested. Comparison with the case of third-order homogeneous Hamiltonian operators, then also third-order homogeneous Hamiltonian operators, by old results, together with Jennifer Pontov and Maxime Pavlov, they are form invariant with respect to reciprocal projective transformations. Then they are classified, but they are classified up to a number of components which is smaller, because of course there is a larger number of coefficients in third-order operators, so it's more difficult to classify them. The variety, algebraic variety that corresponds to them is a quadratic line complex, but it can be shown that these are distinguished quadratic line complexes, and they can be split into the product, the square, indeed, the kind of square of 2 linear line complexes, of the same linear line complex. So indeed, if you classify the linear line complex, you are done. And again, indeed, in n equals 4, the classification of the linear line complexes is the key to the classification of 4-component third-order homogeneous operators. The point is that such linear line complexes, indeed, this is not a linear line complex, it is a system of linear line complexes which can be interpreted again as a linear line congruence. Exactly the same as in the case of second-order operators, with a very important difference. The difference is that while in case of second-order operators, the linear line congruences are given by a 3 form, here the linear line complexes are given as 3 tensors. So there is no longer the skew symmetry. And it's much more complicated to classify them. The classification was found by Genia into a paper of people who were classifying meta-abelian Lie algebra, because in canonical form, such Lie algebra are uniquely identified by the tensors that we need, and they transform as we need indeed. Okay, also third order operators define Hamiltonian systems of first order conservation laws that are linearly degenerate and non-diagonalizable. Moreover, they are they are not integrable, or at least they are integrable only in very special cases. Like in the case of WDVV systems. WDVV systems are all integrable, and a recent paper I showed together with Jakub Vasicek, who was a former student of Artur Sergeyev, that such systems are indeed, they all have up to very high number of components, all are endowed with a third order homogeneous operator. And they are Hamiltonian indeed with respect to such homogeneous Hamiltonian operators, and they are among the few examples of systems which are Hamiltonian with respect to such operators. In the third order case, what happens is that for WDV systems, you always find first order operators which are compatible with third order operators. So the WDV systems are given as a bi-Hamiltonian pair from a bi-Hamiltonian. They can be derived from a bi-Hamiltonian pair. While for systems attached to second order operator, still the first order operators are missing. So we do not know them. Okay, now, sorry, before, thank you, the last slide. So you see that we have a projective geometric interpretation of third order Hamiltonian operators, of second order Hamiltonian operators, of quasi-linear systems attached to them. The remaining problem is what are, under the algebraic geometric viewpoint, first order compatible Hamiltonian operators. I say compatible, meaning that they should be compatible with second order or third order Hamiltonian operators, homogeneous. So compatible means that their Schouten bracket with the third order or second order operator is 0. We have preliminary results about a possible geometric interpretation of such operators, but it's okay, probably this will be another talk in the not so far future. So we have some preliminary projected geometric interpretation, and it seems that there might be further interesting geometric properties. I still have no idea if such properties might be applied to something. For example, there is large use of these operators into the perturbative approach to the classification of integrable systems by Dubrovin and Young, because there is an expansion in a series of homogeneous operators which might be considered under the viewpoint of an action of the reciprocal projective group, but there are still no results, if not very preliminary, in that direction. By the way, this means that if you define an integrable systems using a trio of such operators, then the integrable system will be subject to the action of the reciprocal projective group. But what are the implications of this action is something which is still unknown, completely unknown. Okay, I finished my talk. I thank you very much for the attention, and that's all. Hello?
Yes, thanks a lot. Questions, remarks, comments? Seems that no one has questions.
Sorry, I have, I think, a quick question.
Yes.
I'm Giorgio Gubbiotti. So, Raffaele, thank you for the talk. Can I ask you maybe if something that I didn't got completely? It looks to me that your talk was divided in two very different parts, or the two are actually connected somehow, except from the general ideas of Hamiltonian systems and integrable systems in infinite dimension.
Okay, so the parts to which you are referring are, I guess, the classification of second-order operators and the fact that you can find Hamiltonian systems attached to these operators. They are not strictly related because you can find also Hamiltonian systems which are not Hamiltonian with respect to a single second-order operator, but which are Hamiltonian with respect to a linear combination of a first-order homogeneous operator and a second-order operator. We have few examples of this kind, but I guess that more examples might be generated if one is able to find and classify non-local first-order operators which are compatible with respect to second-order operators. The fact that there are Hamiltonian systems which are Hamiltonian with respect to second-order operators is an important parallel with respect to the theory of third-order operators, because you have exactly the same results, basically, with slightly different geometric properties. And this lets you understand that there might be a general scheme, general picture, which still we do not see in its entirety.
So you think that at some point the non-locality cannot be avoided in any way?
Yes, it cannot be avoided in this kind of approach because the transformation will always destroy locality of the first order operators.
Okay, I see. Thank you.
Thank you, Ralph. More questions? No? Okay, Ralph, thanks a lot. It was interesting, though some things were known before, but all in all, it's quite interesting. Thanks a lot, and I hope it's not your last talk at our seminar.
Thank you very much.
Thank you.
And okay, we will meet next seminars and again and again.
Yes, I'm sure. Yeah, okay. So I wish you a good evening, and we meet as always next Wednesday at the same time. Goodbye.